Picture an archer out in a field, firing arrows at a distant target. Some of those arrows bury themselves right in the bullseye, others catch the edges, and a few might miss the target entirely and land in the grass. That physical act of drawing a bow and sending an arrow flying toward a destination is exactly how a mathematical function works. A function is simply a rule that takes an initial input, like our arrow, and launches it toward an output. If you remember your middle school math classes, you probably learned two specific words. We call the starting inputs the domain, and we call the final outputs the range. But that word, range, causes quite a bit of confusion as math gets more complex. When we say range, do we mean the entire wooden target board the archer was aiming at? Or do we mean the specific splintered holes the arrows actually made? This graphic shows us the solution. To do careful mathematics, we need to upgrade our vocabulary and break that process down into 5 distinct terms: domain, codomain, image, range, and preimage. Instead of grouping everything into inputs and outputs, sorting out these 5 terms allows us to see how the rules of the function interact with the target we've set. Let's apply our new terms to the archer. First up is the domain. This is the set of all allowed inputs. You can think of the domain as the archer's quiver, the specific collection of approved arrows they are allowed to shoot. Next, we have the codomain. This is the entire set where the outputs are supposed to live. In our field, the codomain is the full physical surface of the wooden target board. Then we have the image. The image is the set of outputs the function actually produces. Look at the board now. The image is just that tight cluster of arrow holes, sitting there surrounded by untouched wood. The image is what we usually called the range in early math classes. By calling it the image, we can clearly see how the actual hits differ from the wider codomain. Let's step away from the archery field and see how this works with numbers. Take a look at a specific rule, the function f of x equals x squared plus 5. For this function, our domain, the numbers we are allowed to plug in as inputs, will be all real numbers. Any number on the number line can be loaded into our bow. This animation shows our 2 sets. The horizontal line is our domain, and the vertical line is our codomain. Our codomain, the intended target for our answers, is also the set of all real numbers, stretching infinitely up and down. Watch what happens as we run the numbers through our rule. Because squaring any real number always gives you a positive result, and then we add 5, our actual outputs, the image, will only ever land on the number 5 and higher. The entire bottom half of our target stays perfectly clean. We aimed at the entire vertical number line, but the math dictated that we could only ever strike the upper half. That gap is exactly why we have to treat the codomain and the image as 2 entirely separate ideas. So far, we've only fired arrows, but what if we do some detective work instead? Imagine we walk right up to a specific hole on the target and then try to figure out exactly who shot that arrow. When we trace a function backward from the result to the starting point, mathematicians call the answer the preimage. Let's bring back our rule, x squared plus 5, and do that detective work. If we walk up to the target and look at the output number 9, what is its preimage? This diagram shows the answer. The preimage of 9 is 2 numbers, both -2 and +2. If you square either of them and add 5, you get 9. 2 different inputs manage to strike the exact same hole on the target. Now, let's look lower down on the exact same board and try to find the preimage for the output number 4. The preimage of 4 is what we call an empty set. Because of our rule, no real number will ever output a 4. It's a spot on the target board that is mathematically impossible to hit. Tracing the preimage tells us the full story of an event. It lets us know if a specific result was caused by a single action, multiple actions, or if it could never happen in the first place. Up to this point, the target has stayed exactly the same, but whoever is writing the math problem has the power to change the rules of the game simply by redefining the codomain. Think about what happens if we keep our same rule of x squared plus 5, but we bring out a saw and physically crop the target board so that it only includes the numbers 5 and higher. In this cropped setup, the image and the codomain now match. Our arrows now fill up the entire target space, leaving no empty space on the board. This outlines the workflow. The domain provides allowed inputs. The codomain sets the target. The image shows the actual outputs. This last box summarizes the logic. An image follows the arrow forward, while a preimage follows the whole backward. By distinguishing between what we aim at and what we hit, we see where a rule works, where it fails, and which outcomes are possible.